Record. Okay. Welcome everyone to the October 7th installment of the Propeller 2 Live Forum. Today, Michael Mulholland is going to be talking with us about the P2 EC RevC, the P2 EC 32 megabyte, and maybe the 6410 motor controller as well. So the P2, and correct me if I'm wrong on any of this, Michael, the P2 EC RevC is going to be a demo. The 32 megabyte is the 3D models. And then we are hoping for some pictures of the motor controller. Not sure if those have come in. After that, updates from Chip, open discussion. And if anybody wants to call out things that are on the plan for next week, I can go ahead and add those too. And with that, Michael, are you ready?
Yep.
Okay.
I'm ready.
Now, are you, do you need me to pass you ability to screen share or just stop my own share?
Screen sharing would be good.
Let's see here. Do you have the option to screen share on your menu?
Just trying to get that going now. Okay, here we are. How's that for resolution?
Looking good.
Awesome. Okay, well, thanks, Andy. So, yeah, so these are the new RevC boards, which I don't know if anyone's seen those before, but they do exist. They are running through manufacturing today. In fact, there may even be some sneaking onto the web shop as we talk.
Yes, if you refresh the web page, you may see them come into stock. Just keep refreshing, and the hope is that they'll appear in stock before the meeting's over.
Yeah, just glancing at that, can see they've not quite made it in yet. But anyway, yeah, so I just wanted to, yeah, as Andy said, just sort of run through the new features, and if anyone has any questions, we could try and help with those. But yeah, so there's the modules running away, and we don't have a great amount of code going, but I could probably just at least show that the things are actually working. Oops, if the camera goes up a little bit. Yeah, that's probably back to front though, isn't it? I suspect.
It's legible on our screens. I can see the clock freak, and
it's not mirrored on our screens. It's just mirrored on yours.
Okay, brilliant. Well, that's just running at 360 megahertz, which was the, I know there were some issues running at such high frequencies on the previous rev. So just to demonstrate that that's been dealt with, and that's one of the things that was covered in this rev.
That is fantastic. Wow, 360. I mean, I think that's because we have super stable power supplies, and it might make a difference that rather than using a crystal, we are using that sharp-edged VC TXO or whatever it is. Can't remember all those letters, but anyway, there's going to be, if there's less jitter on the clock input, there's going to be less jitter in the final PLL. And as long as we don't get underneath that minimum pulse, the chip continues to run. So this lets us take it higher because there's probably less phase jitter.
Yeah, no, absolutely. I mean, that's obviously one of the key changes to make. Slide this thing back down and get the board in view. Oh, well, we don't really need that red cable. Okay. So yeah, so well, we may as well start with the clock then, because obviously that's one of the key changes, and that's down here on the bottom right hand corner. That's a 500 parts per million clock Chip can probably remind us how well it will keep time, but we really wanted to make this the ideal microcontroller module for real-time applications, industrial and educational. I can see Gavin's there, and I think he'll probably be using it for clock projects in the classroom, hopefully with some interesting mechanical parts running at the same time.
Yes, we've used real-time clocks with temperature compensated crystals and stuff for things, separate modules. So I'm really looking forward to this kind of Rolls-Royce version of a clock for this.
Yeah. Well, that's absolutely the target. So yeah, so that's going to be fantastic. It'll really open up doors to that.
It's off like just over 1 second per month.
Mm-hmm.
If it's at the 500 part per billion limit. So it's like 15 seconds a year, but it's probably going to be within that, you know?
And what would you expect to get from a typical off-the-shelf, not a specialized, but off-the-shelf real-time clock module?
Well, if we're like maybe, I mean, we had it down to 10 parts per million, so that's 20 times the error, right? So, but the crystals we're using have been rated for 25 parts per million. I think that's normal. So that would be, this is 50 times as accurate as 25 parts per million.
Yeah.
So
I can't
agree with, if you do like instrumentation stuff with this, and you have like a good quality frequency counter or something, there should be like a real high degree of correlation. You should get good 7 digits of agreement on timing.
So the one I've been using for years, the DS3234, there's a breakout from SparkFun I use for $22.50, has only plus or minus 2 parts per million. So this is fantastic.
Yeah, it's 4 times better, and it's within that somewhere.
Excellent. So that's yeah, so that's the clock thing. And then we've got over on this side, we've got the new wider voltage input. So it'll now accept 5 to 16 volts in. So we've kept compatibility with the existing breakout boards, such as this one and the Johnny Mac, which is affectionately known as the footlong in some circles. But yeah, and it'll keep compatible with those, but also with the upcoming as yet top secret future boards, which will target some wider voltage range inputs as well to run servos and things, as Parallax is well known for. So yeah, so the new voltage range is really important on here. There's actually an EMI filter on here as well, which is essentially the yellow capacitor you can see, and a filter just before it. That's to meet EU standards for emissions. So this new module has very low conducted emissions outputs, and
yeah, Michael set up a whole like EMI testing. What would you call it? Like a little cage. It's kind of a Faraday, most of a Faraday cage, and he has all these instruments, so he can do the EU testing at his site. And so he put these filters in there, and everything is like way below. We're like, on most things, we're less or more than an order of magnitude below their requirement, right?
Yeah. It's very close to the floor, and yeah, we'll publish that soon. We're working to get quite a lot of data together for the manual. We don't want to rush it out this time, but you know, over the space of the next few weeks, we'll have all this coming out. So yeah, so that's on there as well. So I mean, especially for industrial applications as well, that's going to be key. And then moving up the board, we've got, well, there's 2 switching power supplies there. So because of the wider input range, we needed an additional switcher to power the LDOs, which are around the P2 chip. You don't need to go to that extent. And if you had your own application, you know, you can decide how you want to do the power. But for this module, again, we wanted to make it as universal as possible. And so we've got 1.8 volt switcher on one side, which is to power the core. That stays the same as with the existing edge modules. But we've now got a new 3.8 volt switching regulator next to it. Both of those will pump out, will Well, they're guaranteed rated for 2 amps, but they've been pumping out 2.5 amps in testing at moderate temperature, room temperatures, no problem. They provide power to the LDOs, which are around the P2 chip, which are the same configuration as before, but we now benefit because we've got much lower voltage in going to those LDOs. We've therefore got more efficiency and less heat generated by the voltage drop across those LDOs.
Right, because they're only having to drop like 0.5 volts now, which is plenty of overhead. They're spec'd, if they just have 100 millivolt spread, that should be sufficient, but we're giving them 5, so they should be able to respond very quickly, but that's still not so much that they're going to get that hot. Yeah,
no, absolutely. Well, we've done that because of to make sure that the LDOs can deliver the current as well. They'll deliver well over the rated 300 milliamps that we've got in the guide. We've tested them at 500 milliamps. They're stable. I actually know that they start to wobble around 600 milliamps, but no one should be pushing them to that. And we don't spec them for that, but they absolutely deliver the current well within tolerance at over 300 milliamps. So they're fantastic. Again, user projects, if people are tapping off 3.3 volts, we want to be able to deliver the best we can, without the area around the P2 chip heating up unnecessarily. So that's another big improvement. And then above the switches, we've got, sorry, the lighting's a bit.
Hey, wait, Michael.
Let me just,
about a couple more things about the switcher. So they have this wider common input range now. So you can run off 12 volts if you want, which is nice. And then you see this, I don't know if you can see this board, but okay, this had the single switcher, right? And it would just use the LDOs to drop whatever was coming in on the 5. But remember these, I don't know if you can see this. This is a ceramic inductor. It's like a ceramic body inductor. Remember how these things would fall on the table and break. So now Michael's got some really nice, like monolithic epoxied that was the old inductor that would break. But now on the new board, he's got these really nice, like monolithic parts that look like capacitors. Yeah, that's still, see, there's a broken one. See that they have. And that's then when it breaks, it doesn't work that well because it changes its inductive qualities.
I think I might have nuked your screen share when I tried to pin Michael.
Shall I just share again?
Oh, I see it. Does anyone not see his screen?
I'm seeing it just fine.
Okay. Thanks, Andy.
Yeah, sorry about that.
That's no worries. It's better to know. So as Chip was saying, so these are the new inductors here, newer technology, big difference.
Yeah, and they go at like 2.2 megahertz now, right? Whereas before, what were they? Like 1 megahertz?
They were 1.5 before, 1.5, the existing switches. So these are now 2.2 to 2.5. It'll vary with the load, of course, but around the area. Very nice. And actually the higher frequency obviously is is one reason why they can be smaller, but they're just also newer technology. These epoxy inductors are just much smaller.
I think it really shows up in the fact we can run right up against the speed limit now.
And we can hang a dead load of both of these, and they'll pump out well over 2 amps that they're rated for without dropping voltage.
That's only a couple parts. I know Michael spent a lot of time and thought to make it the way it is. And Doug was in here a bit ago. He's running the machine shop, and he's going to use the P2 Edge on some project it'll probably have a high sale price. So it's not super critical, but he was saying, well, I could just buy the chips. I mean, if the module's this much, how much are the chips? And I was telling him, well, the chip might be what, 15 to 20 bucks. I don't even know. But the module has solved some engineering problems like not just these power supplies, but there's that clock issue, and there's a really good via stack to get the heat to the back of the board. So this is like, if you can afford to buy the module, it makes good sense in a product because it's going to be very stable and you're going to get the best performance out of things because you've got good power supplies, good clock, good heat spreading that you're probably not going to get on your own simply because you're just not going to invest the time that it would take to do something like this.
Yeah, and for a lot of applications, you might not need, a multi-layer board. You might just want to, you could, for the customer application, you could just buy the socket and have that on a standard 2-layer board, which are much simpler to and lower cost to manufacture. Especially
Right.
if the customer board is huge. I mean, this little thing doesn't really make a difference. But if you compare it to this thing, just to actually have, just to pay for a PCB that size, is a huge cost, especially if it becomes 4-layer or 6-layer to support a processor. Whereas, the processor might be the only thing on the entire board that needs multi-layer. The rest of the circuitry might be quite happy with a 2-layer board. So it certainly can make a lot of cost sense, in industry, just to stick to cheapo 2-layer boards for your application, your front of your washing machine or whatever it might be. You might need a huge PCB for that, but you don't want to pay for multi-layer. So yeah, I mean, the modular solution, which takes care of all that for you, is a great way of solving that.
Yeah, I think it's the best approach because we've been through a lot of iterations on this so far. We keep refining it, but I think we're like asymptotically up against about the limits of what can be achieved.
Yeah. Well, we have changed the arrangement of the parts on this as well, specifically to make best use of the layers and to improve thermal dissipation through the layers. You can see that if you compare that to the older Rev, the flash and the dip and some other parts have moved over to the other side to allow us to improve the routing and the layer stack. So yeah, well, that's one of the reasons. The other reason might be obvious later. Yeah, so that's that. And then we've got so the flash is the same as before, so that remains standard. And then the dip switch settings are all the same as before. And then so the micro SD card's another new thing up on the left-hand side there. So you can boot directly from SD, and that just accepts standard micro SD card. And most of you are probably familiar. You can just boot from SD with that. So it's great for in-field firmware updates and or even for end users to update firmware or to use it for the usual things such as logging and storing audio, video data, that sort of thing, where you need huge capacity. So yeah, micro SD now on board. Yeah, so I think that's the front, and then on the back we've added a table, so you can now refer to the back of the board to see what the boot mode settings are for the dip switch, rather than having to refer to the user guide. They're now printed on the back of every module. So that's a change from the previous board. Oh, and we've removed the optional breakout pads for programming, as we realized that was one of those things in the design process that seemed like a good idea, but in practice, not very useful. So we removed those, which enabled us to improve the layer routing as well, not having those there. Those are, just the prop plug programming breakout pins, but because they're already here, there's not really much sense in having them there. So that is the new RevC.
And I should mention that they are now in stock, and that I pasted the web page where you can get them into the chat. It's www.parallax.com/ /product/p2-edge-module.
Awesome. Thanks, Andy.
All right, so that's good. So we finally got this P2 Edge RevC thing all done.
Yeah, it was a bit of a challenge because we had some unfortunate issues with the manufacturer along the way, but we've persisted through. We've actually partnered with a new PCB fab, and they have higher density capabilities in-house. So moving forward, I think we're going to have a much better time with these products. Yeah, but we'll start the thermal testing over the next week. So over the next sort of 1 or 2 weeks, we'll start to get that data. We'll share it here and on the forums first, and then it will start being brought into the P2 manual effort, or should I say manuals, because there's so much of it. It's going to spread into more than one manual. But yeah, so here we go. But it'll run faster than the previous Rev, cooler as well. We know that. And obviously it's got the extra features, wider voltage range, micro SD card, and the new clock.
Hey, so Michael, have you got anything about that one with 32 megabytes?
Yeah, I can show you.
Was that going to be next on the agenda?
Yeah, I was going to show. I don't know if anyone had any questions about that, or should I?
Oh yeah, take questions if anyone has any.
Maybe not for now.
One quick question. So one thing that a student asked me about, and I looked it up in that really wonderful document that you'd written for the last version of the Edge, was how the LEDs were buffered on 56 and 57. So that's just something to point out as kind of an interesting feature, that those don't have anything to do with the output of the pin. They won't suck any current.
No, they go, the way that whole thing works is there's a dual inverter, because there's 2 pins, right? P56 and P57. So it's non-loading. It's just a CMOS input. There should be no, I mean, there's probably going to be a slight, maybe nanoamps of pull because of the protection diodes on the inverter chip, you know, that are leaking somewhat, but nothing, there's no like load to anywhere. It's just pretty much open. And then that chip is always on. And then the dip switch controls whether the LEDs are pulled to the power. So if that dip switch opens, the LEDs don't come on because there's no voltage across them, even though the 1Y and 2Y outputs could be high or low.
And I also see as a feature of this new RevC that they're white now instead of green, which is cool.
Yeah.
Yeah.
I noticed that when you plugged it in, Michael, at the very beginning. Yeah. Very cool.
Yeah, I think we actually changed the color on the Rev B as well. I think the Rev A were green. I can't remember.
I've had the Rev A. So.
Yeah, that would be why. I think Rev B were white from the start, although I can't quite remember now, but I believe they were. Yeah. Yeah, the cool white LEDs to go with the white silk screening.
Very cool.
So let me just find the 3D model for the new one. So this is the 32 megabyte version. These boards were ordered a couple of days ago. There's a 30-day lead, unfortunately. So we're looking at, where are we now? 7th of October. So we're probably looking mid-November for these things. Oh, where's the 3D model gone? There it is. Okay, we'll just zoom this in. Hopefully that's clear enough. It seems quite dark to me. Let's move that over there. That might help. Is that clear enough to see?
Yes.
Sure is.
Yeah, so I mentioned earlier that there was another reason for moving the parts around. The main reason was to improve the routing, but then we also realized we could have a kind of consistent family of layout, if you like. And so this is now the flash version, and you can see from the front, it's hardly different at all, apart from the text, to the RevC that we've just looked at. Component-wise, the 4 memory chips are added along the top here, and we've changed the numbering of the 2 LEDs, the pins to which they're connected. And I'll explain why that happened.
Those are the new last 2 unused pins.
Yeah. So what we've got is so there's 4 8 megabyte PS RAM chips there that could be addressed as a 16-bit bus for maximum speed, but they're wired in a way that they can also be addressed individually as 4-bit devices. I don't know, Chip, have we got any data from the prototype on bandwidth or anything like that that might be interesting to know at this stage?
Bandwidth on how so?
For how fast the chips are running in terms of data back and forth, data I/O.
Do you mean on the chip or these memory chips?
No, to the memory chips.
No, I don't know. But I mean, you made like balanced length traces and all kinds of stuff, right?
Yeah.
So I don't know. I mean, they should be all very coincidental. And I don't know. We don't have one of these built yet, do we?
No, but no, we haven't got one of these built, but we had the prototype on the RAM chips. Maybe that's Roglo that was working with those more. I know the chips are rated at 133 megahertz each at this voltage, 3.3 volts. Anyway, we'll get to that. So so there's the 4 chips. The clock select and the chip select or chip enable, as sometimes it's called, and the clock traces are all matched. But we've also included a series resistor and a optional capacitor on the clock line. The resistor
so we can tune it later if we need to.
Yeah, I mean, we're going to tune it at first article stage. When we have the first panel coming off production, we'll test this. But provisionally, they'll ship with 0 ohm resistors in there and the capacitor unpopulated. But if we find that we need to tune it, then we'll be ready to do that before we start shipping them to everyone else. So that's that. We've included that safety net, but we have balanced the traces to clock and signal, and the data traces are balanced as well. Mind you, the data traces, my understanding is that's less crucial because the P2 will always wait for the last bit of data, if you like, to come through before it then proceeds to the next step. So the crucial thing was to get the impedance and the trace matching right on the clock and the CS, more so the impedance probably. So we've squeezed in those tiny little flash chips there, which gives us 32 megabytes. In doing that, we've used up some of the pins. So that's why the label on the front still has 8 core, but now it says 46 IO plus 32 megabyte. So the 40
you must just be dyslexic and you transpose the 60 and the 4, right?
Well, it was just magical, the number. So so we've got 46 IOs left available. Plus 32 megabyte.
So that's 64 minus 18. So where those 18 pins went is 4, 4, 4, and 4 data. So there's 16 data going to all those. And then there's the clock and the chip enable. The clock and chip enable are common to all 4 of those things. So that's where those 18 pins went. So they are not routed out to the connector, but Michael routed them so that all the wires are of equal length on the circuit board. So we should have no like PCB related problems. There is a little bit of, there's less than 1 nanosecond of like 850 picosecond distal delay between the earliest and latest IO pin. And I don't know where those pins are, if they're up in that range, but anyway, there's that to contend with possibly, but we hope to be able to skew the clock with that RC circuit so that if necessary, so that we can get the timing to be optimal at, you know, at all frequencies. Well, should I say that at all frequencies? I guess so.
So in terms of the IO pin availability on this, we've got, and the reason that the LEDs have moved is because we wanted to keep continuous banks of 8 IOs available for the end user, as many as possible. So you can see on the front, we've got P03 through to P30, is it 32? No, 31 it would be, wouldn't it? So P0 through to P31. So you've got 4 banks there. And then the next bank.
Yeah, you have one more full bank. The beauty of this was that it gave you 5 full 8-bit ports before it started stealing pins. So it worked out really nicely because 56 and 57, the CS and CE were they were the first 2 of the last 8, which have all the boot functions. And then the 16 below that were the data lines, which are now labeled, you see no connects. So it worked out really nicely. So you give P0 through P39, and then you've got some up top, but everything that goes to the RAM, which is super high frequency and really couldn't tolerate the additional loading of, you know, coming out to the edge pin, and then who knows where after that, right? We don't want that going down the Johnny Mac board and skewing. So what needed to be erased from the connector was erased to make everything like impedance known and constant that relate to the PS RAMs, because those are going to be clocking at probably 100 and up to 180 megahertz.
Question for you: do we have a way to recognize programmatically which board this is?
There's one way of doing it with one caveat. So the P57 is going to have a 100K pull up, and with the with the RevC, with the non-RAM version, P57 does not have a pull up. So you could use that in a specific customer application, but you know, it's only going to work if the customer hasn't connected something externally to IO P57. So, you know, you can't guarantee it for everyone, but in a specific customer application, it's possible that that's usable. However, the other way is just to try polling the RAM and seeing if you get a response from the RAM's ID. You could just poll one of the RAM chips. So that might be another way of doing it.
Yeah. Yeah, so there is that 100. And what pin is that on?
P57.
Perfect. Okay, so that is the highest one that would be uncommitted if you didn't have the RAM. So if you see a pull up on what would have been the last free pin, so that's kind of it's not very, you're not going to tickle too many things if you just check that one pin, which was the prior top free pin anyway.
Yeah.
Better than P56.
Yeah. Well, you know, because it was previously used by the LED, it's also possibly less likely that someone will add an external resistor or something to that part. Yeah. Anyway, it was kind of there, so we thought we'd kind of use that, and for the possible future Wi-Fi module, we also thought that, well, we could change this pull up to a 75K, and then using the P2's internal ADC, you could again determine the value of resistor. pull-up resistor on that pin to again enable you to determine which board you've got. That said, you know, if there's a Wi-Fi module with RAM, you know, you could poll the RAM to see if you've got RAM there. You could probably also talk to the Wi-Fi module to see if it's there. So there will be other ways of determining your module. But you know, it just gives that flexibility for your, depending on your application. So let's go back to that image. Yeah, so I think you can see now why we've moved the LEDs to P38 and P39. As Chip said, they're the last two available pins, and they're on the back of the board, so they're not going to interfere with the continuous pins on the front. They're just nicely tucked out the way. So on the back, we've kept the voltage outputs that are you know, needed, but we've taken away the ones which are only used by the RAM, so that you know, the voltage bus can't be messed up. And the programming pins are there, the same as they were before. And then we've got the table. Well, the boot mode table is the same as the new RevC, and then we've added the pinouts for the new RAM chips as well.
This is very nice.
Michael.
Thanks, Mike. Yeah, thanks, Michael.
Yeah, and I think this thing turned out just right. I can't think of anything that should have been done differently. I think Michael and I went over it and over it and over it and debated like the smallest minutia, but kind of finally came to agreement on everything.
Yeah.
So are these boards are out? They're ordered already, right?
Yeah, the PCBs are ordered. We've got a 30-day lead time. Yeah. So I guess mid-November. Yeah, mid-November, maybe towards the end of November, they can be. I mean, as soon as they arrive, they'll be through manufacturing, obviously. So yeah, end of November in the store, I reckon.
Okay, end of November. Okay.
Michael,
Hey, Henrik.
please, the capacitor for the run chips to retard the clock pins, do you plan to use MPO capacitors to keep them from varying too much with temperature?
Are you talking about the decoupling caps or
No, the delay cap to adjust the clock signal to match the maximum transfer speed for the runs?
Yeah.
You said that that capacitor will not be mounted. Yes, it's empty. Okay, it's unpopulated. So that capacitor will be of the NPO kind. So you can be ensured that it will not vary the capacitance too much with temperature. Is that right?
Yeah, I mean, because we've not fitted it, we've not really given that much thought, but thinking about it now, then yeah, it would be an MPO because of the heat of the P2 next to it. Yeah. It would need to be a really a cap with really good temperature tolerance. Yeah.
Okay.
Yeah, I'm going to write that down so we'll make sure that that's not missed if we do have to add something there. Yeah.
You will be using Roglow's driver to test those runs to scan for the maximum speed.
Yes.
Okay.
Yeah. That's what we'll be working with to start with. Yeah, we sent Roglo the PSRAM prototype board that we made before starting on this project.
Yeah, so you are not working on it, Roger is doing it.
Michael, are you still there? Or did you disappear?
Yeah, I'm here. I was just trying to. I didn't catch what Michael said. I was just processing it, but it didn't come to me.
Yeah, what I said is that you are not working on it. You let Roger work on it because he is into his driver. I mean, that thing is a bomb. What he is doing there.
We don't even know what Roger's doing.
Yeah.
No, but what
Yeah.
I saw in his code and what his driver is already doing, I mean, come on, this guy can squeeze code into one cork. That's unbelievable.
Yeah. Yeah, no, absolutely. You know, it's definitely, yeah, he's the man for the drivers. So,
Roger, Roger has found another 2K bytes of run inside the cog and didn't share with us. There is a hidden 2K extra, 2K extra of run into his ships, so we can stuff much more code without telling anyone where he gets all that space.
it sounds like he's found the secret debug memory. Yeah. So there we go. So that's that'll be the next one coming up.
Yeah, and you know, to summarize, this is exactly the RevC board, but with those 18 pins routed to those 4 RAM chips and not connected to the edge connectors. That's the only difference.
Yeah, and the 2 LEDs
Oh,
renumbered.
LEDs moved to the new last unused pins.
Yeah. Yeah, yeah, exactly. The last 2 pins on the of the available IOs.
And Michael and I were thinking it's too bad we just didn't use P0 and P1 in the beginning. So it wouldn't have this migratory LED pin thing.
Yeah.
I think those would be the most popular pins. I know that you like all the pins to be kind of agnostic from hardware, but that pin 0 and pin 1 are the first pins people ever use.
Yeah, you're right. Right. So we figured, this should probably be the least loaded then. But really this inverter doesn't load, but it's still better to have nothing there.
Yeah.
So I'm wondering, are there any kind of killer apps for this board already in the queue that that we're going to use this high speed RAM? Is it video? Is it are there already some things that just so we can help sell this new board?
So
Roger has his video driver working with whatever output you want to have out that video driver, and it can connect to the RAM to get the video RAM out of the hub. So you basically can use that hyper RAM there as a video buffer, video for all those whatever you want. Roger did a basic mean job. You can connect whatever display you find and it will work. Composite.
So from the SD card, so large video files with the SD card buffered.
And the whole video RAM would be in the external RAM. So you have the whole hub for yourself, or most of it. And he also built it that one cog or whatever can use with the priority, the hyper RAM, and the other cogs can still access the hyper RAM also for own purposes. This driver is honestly a bomb. I'm still digesting it. It's complicated code. But what he has in there is amazing. So basically you have the HyperRAM as a video RAM buffer, and all the other cogs can still access it also on different areas and without conflicting. The video access has kind of a little bit priority before the other ones. It's very smart stuff he is doing there. I think I'm a good programmer, but I'm bow deep. I'm bow deep, Roger. I mean, yeah, he is doing good stuff there.
So just to catch me up, is that going to be to an HDMI output or is it analog? And what are the resolutions we're kind of looking at with that? I'm just trying to think of the applications of where we can take this.
The same driver can drive HDMI, composite, VGA, RGB with different settings and different resolutions. And he also added a display list thing, so you can say the top 20 lines should be in this resolution, the next 20, 40 lines on should be a text display. It's just stacked horizontally, so you can't do side by side. It's just slides, but you can put different graphic areas, different resolution, different colors in slides down the screen. And those display lists can basically then fetch their information out of different memory areas. So you can have a text buffer where you write stuff in and it will appear in the upper left, up down part of the screen, and kind of a graphic on the top and in between, whatever. But it's just slices. It's not windows. It's just horizontal slices. But there you can change the resolution and also say this content comes out of HyperRAM, this comes out of a hub buffer, this comes out. They don't need to have continuous memory. They can be completely separate buffers where you fetch your data, and it can be in bitmap format or in text or even tiles. I think I even saw tiles. I'm not sure. This and all of this in one fucking driver. I mean, it's unbelievable. He should make a presentation for that soon, and I think he will do as soon as he has that HyperRAM stuff in there. I mean, he already has it tested with those PS RAMs, and it's working. So we need Roger to make a presentation of his driver, because I barely understand what it's doing, and I'm fascinated. You know,
Yeah,
It's really neat. Sorry, go ahead.
Yeah, I was just going to say that once we can get Roger the the final board, then he'll really be able to make his driver rock, because I think he hit a limit that the prototype was limited in how fast he could, because of the layout of the prototype, he was limited in how fast he could push the RAMs. So he kind of, I think he'd done as much as he could, and he just kind of needs the final version now to be able to really polish it off.
And do we have a polished SD card driver at this point? And is there a maximum size for that? I know they have different formats as you get to larger and larger SD capacities.
I have one that works in quotation marks. I don't think there's one that's actually polished though.
Is there a limit to how large of an SD card it can work with?
No. You can, well, the ones above 64 gigabytes and above, they come pre-formatted with exFAT, and that's the problem. But you can just reformat them to FAT32 and they will work until like 2 terabytes or something ridiculous size.
Oh, wow. Okay. Great.
And of course it will work down. Actually, does it work down to the low size ones? They actually have a hardware difference, or not really hardware, but like interface difference. And I think the boot driver actually doesn't support them, which is very stupid. At least that's what I think. I think it doesn't support them. Like the boot code, I don't think it supports the small SD card.
Yeah,
other
you might be right, Ada, because because with the spin driver could support the FAT formatted cards. And isn't that the issue, that the larger cards you can't format in FAT, and therefore
But you can format any card in any format you want. The problem is that the small cards, you address them in bytes, even though you can't access, at least on most cards, you can't actually read at a byte granularity, but you address it like the byte granularity. Problem is that only goes up to like 2 gigabytes or 4 gigabytes. I don't know. There's a limit to how much you can address in 32 bits. So what they did with the newer cards is they just made it per sector addressing like it probably should have been from the beginning, and that's how they can address more memory. And you have to actually handle that difference in the initialization and then of every command.
Those cards below 2 gigabyte or something like that, which use that byte addressing scheme.
Yes, 2 gigabyte and below is byte addressing.
But I think with the newer cards, you basically can skip that part. I mean, I think FSRV and Kai still support those byte addressed sectors, byte addressed cards, but everything below, everything above 2 gigabytes is already sector addressed. So we can just skip the byte addressing.
It's not a big deal. It's really not a big deal. Just a slight bit more initialization code, and you have to store whether you're using an old card or a new card, and then, well, I say old and new. They still make 128 megabyte cards, I think, like really cheaply. Probably terrible performance. Mind you, I think the one that Michael has got on screen right now, it doesn't look like a good card. I think the good ones, they have so many logos of like sort of standards that they satisfy that you can't actually tell what, anything else, because there's like the A1 logo, there's the C10 maybe. I don't think they even put, no, I don't think they put the C10 anymore, because A1 implies C10, and I think no, you have V10 and V30 and V60. I think that's the ones. There's loads of logos on the good ones.
Yeah, but basically, the byte addressing scheme was below, I think, 2 gig or 2 whatever, and is not really used in those bigger cards anymore. And the other thing, which is you can read out those configuration registers of the card, which basically tells you how much speed it supports and stuff like that. There are a couple of configuration things. If you look at the FSRV code, you will find that they read it out to check. It's a couple of years ago when I did that race board where I had kind of 4 SD cards on a P2, P1, and there's a raised array. So that was a time where I kind of was playing around with SFRV and Kai's driver, and both of them read those config registers they don't do much, but there is standing in a lot of information about how fast the car is and the card is and stuff like that. So basically you can figure it out, but in my opinion, a driver for a P2 should just skip the whole byte addressing shit. It's not needed anymore.
Yeah, I was just looking on the GitHub to see if anyone had added a fleshed out SD card driver. I'm not seeing one, but
I do have one on the forums, and it's what I use for the spin hexagon. I actually hacked it together from like 2 or 3 other drivers, I don't know, because all the other drivers were having issues of some extent, and I also had to add my audio stuff that I needed onto it. So that's how that came to be.
Yeah, I was just quickly having a look at the because actually the parallax test procedure for the edge modules runs on this SD card. That's why that one was out, because I was testing it before sending it over to manufacturing last week, and it's still in there. And so that must use some sort of
SD from 2 GB.
Oh yeah, absolutely. It boots from that card.
I thought that didn't work. Maybe it works in the boot code. It doesn't work in something else. I don't know. I don't remember.
I just wonder if the size would be smaller because 128512, maybe that's the limit. And after that, they switched over. 2 GB seems
It's
too high to me.
definitely 2 gigabytes. It's definitely 2 gigabytes.
Interesting. Well, that certainly boots because that's what I've been using for testing the.
Though God knows what these like. Is this a brand card? I can't read it because if it's like a no-name weird card, then it might just be like might just be a new kind of card, but with 2 gigabytes for some bizarre reason.
It's a Toshiba. Well, 2 gigabyte micro SD.
Okay,
There's no other great markings on there.
Well, Toshiba, I don't know. It may just be a rebrand. I don't know. I don't think.
Yeah, but basically below 2 gigabytes, they used a different addressing scheme, and then they switched over to sector indexing. And then I think the best implementation for the P2 is currently, I think Rayman did it. He did an either Rayman or Cluso. They did that FSRV version, which basically needs a block driver kind of sector addressing. And
no, the FSRW in my experience is terribly broken.
Is it?
Yes, it,
I mean,
it was
I
having
haven't
weird
tried
issues
on the
with I think the issue was that I wanted to create a file, but it didn't properly create the file. I'm not sure if I ever got to the bottom of it, but I replaced it wholesale. So
but my best bet, I mean, I did that, I don't know, 4 or 5 years ago with my race system. I basically, FSRV had that nice block driver from LoneZock, and I basically remodeled Kai's driver to use the block driver from LoneZock because it does a write behind and read ahead and is kind of nicer. But basically, most of the stuff in Kai's driver is bar spin, and that should be kind of transferable to.
Yep, the one that I made is basically just Kai's driver. I think it's slightly modified. I don't know. It's ported to spin 2, and I think Cluso originally did it. I don't remember it.
Yeah, but he did it in spin completely. He didn't wrote in Puzzle driver for the SD.
Yeah, I just hacked I don't even know who wrote it, but someone wrote a block driver, and I fixed some bugs in that. In particular, I don't remember. I think the bug was that that one of the timeouts was completely bugged and was just not working right. And anyways, I made it work, and it also does audio for some reason.
But basically Kai's driver has a better support for, and in my opinion, more complete than FSRV, but
you get directories
faster, yeah.
Directories, unbelievable.
Yeah, FSRV does directories too. You have just to trick it a bit.
Lately, I think when I received the RAM module, because Ken has promised me one, but I think he has promised me one. I think that's when I'm gonna start the 68,000 emulation ping that I've been wanting to do for a while, and I guess that could be a funny thing. Perhaps not a killer app to play 30-year-old games, but you know.
I have started 68,000 emulation, and I found a really nice data sheet from Motorola describing every command and up 68,000 up to 6850 or something. It's a really nice document. If you are interested in, I can send it to you. I started with my X-Byte, but I failed, and then I lost interest. So
you can't really do X-Byte with the 68,000 because
because
you kind of have to jump around the instruction word with what you pass.
exactly there I failed. I try to use that XByte thing, but it doesn't work with them opcodes. So I kind of abandoned the project. But I had
There's
that
so many
really
stupid
nice-
special cases, so many.
Yeah.
The stupid ones are
But
really
they
easy.
have-
Most operations on A registers do not set the flags. All the other addressing modes do, but A register address mode, no flags. But only on some operations. Some other operations I think do set the flags.
Yeah.
If you do post increment or pre decrement on A7, it will always increment by at least 2, never by 1 if you do byte addressing mode.
Yeah.
That is another
Yeah,
funny
but I really have a document. I have to look at it. I have to look for it.
There's a lot of weird edge cases in the instruction decoding, like where sometimes instruction is not allowed in a particular address mode, and that instruction, if it were encoded in an address mode, actually encodes another instruction. It's complete madness.
No, it's not that bad. I told you I have that one document which has some opcodes really nice explained in which groups they belong and why. I mean, I have to look for it. It's maybe 2 years ago.
I'm just thinking there's a reason this instruction set kind of died out and was like replaced by ARM and PowerPC, because those aren't like completely terrible in terms of how the instructions are decoded, and that's really the thing that bites you when you want to scale it up to superscalar, is that you need to decode pretty much all the instructions in the pipeline to figure out how they depend on each other. And when every instruction is decoded like that, it just goes completely off the walls.
I tried it with that Xcode thing, but it's not really meant for, because it's you can't decide on the first byte where you have to go.
You can decide on the top nibble. You can decide on the top nibble. That's kind of the instruction group, right?
Yeah, and we would need a nibble Xcode and not a byte Xcode.
What you really need is a extract arbitrary bit field instruction, like
yeah, exactly. I kind of got stumped on that nibble thing, basically, and then I said, well, Xcode is not a good idea to try that with that bytecode.
It wouldn't work with XByte anyways if you're executing from external RAM, because where's the code coming from? So what instead would need to happen is, I think the DMA transfer from the RAM always comes into hub RAM because reasons. But you'd have to read it. I think the ideal way is to read it back in one block, and then, well, I've wrote about this on the forum. You'd have to fetch a big block of instructions. By a big block, I mean like 16 or something. So the individual accesses don't like slow it too slow, and avoided the explicative there. Then you'd have to figure out when you're branching whether it's inside that block, and then you can do really fast loops, kind of like the 68K10, the 68010. How can you just not have shorter names for things? Motorola, please go back to the past and make your model names less obnoxious to say. Anyways, you'd have to you could do fast loops to kind of counter out the slowdown that's inherent to external memory access.
I'm not sure if our
Okay, Anna,
I was just thinking of showing that. Oh, sorry. I was just wondering if anyone wanted to have a brief look at the upcoming motor controller, and I was just thinking that the name for this is quite long-winded too. So I hope we're not in the Motorola line of thinking. But if anyone's interested, I could. This is
Yes.
This is going into production. Oh, it's actually in production right now. So maybe next week it'll be in the stores.
I
Yeah, it's it.
emailed Pharrell, but haven't heard back. I was hoping you'd have a picture for us.
Uh-huh. Yeah, I just read an email as I was talking from him to say that he's not going to have a picture today because he's working on the pick and place machine, but it is going through possibly tomorrow. He'll have some pictures for us. So for next week, well, for next week, hopefully it might even be in the store. If someone hurries up and writes the user documentation. Anyway, so yeah, so this is you know, an add-on to enable us to test the motor.
Michael, there's enough room on the outside, like beyond those two header connectors. There's not any kind of interference problem with anything, is there? I guess that'll fit on all of our boards.
Yeah. No, it's interesting you asked that. It'll fit on most of the dual headers. No problem on the eval board.
Right.
I think on the Johnny Mac there's one dual pair that it won't fit on because of the location of the capacitor. Yeah.
Well, I wonder. Okay, let's see. We probably could have. Maybe we should have designed that so we just clipped that thing back a little bit, right where the interference would have been, because there's probably nothing there anyway, right? Except the names, the silk. That's okay. Whatever.
Yeah.
It's okay, but that.
I know that we specifically looked at that, and I know I've got a. I know I had a drawing somewhere marking out all the, you know, keep out zones and the maximums and minimums, and to be honest, I just can't remember. It was so long ago.
Both of you are saying that it's a capacitor causing the issue of fit. What do you mean by that?
Oh, just on the. I can show you on the picture here. I think that video is still working. Yeah. Just on the Johnny Mac board.
Oh, the capacitor on the Johnny Mac board itself.
Yeah, this one here.
Good, I'm with you.
I actually can't remember now. I kind of feel like we made it fit, but if we didn't, then this will be the header that you won't be able to plug it into because of that capacitor.
Okay, the same for the opposite side of the board as well. Then.
Yeah. But I think, yeah, I just kind of have a feeling that we made it fit in the end. But, you know, it was like so long ago. It just, things have just seems to be taking forever now because we've been waiting for the MOSFETs to come, you know, stuff that should have been delivered to schedule. And then the supplier just whipped the rug out from under us. And, you know, a month or so ago just said, oh, well, now we're not going to deliver them when we said. Just-in-time manufacturing has just gone out the wall, really. I suppose it just, yeah, it's just failing because there's no consistency, is there? There's no consistency of demand or supply. So it just, yeah, absolutely, yeah, it fails. But it's really a problem when you've got, you know, you've got trust, you know, with long-time trusted partners, you've got orders in place and schedules in place, and then, you know, they just turn around at the last minute and say, okay, tough, you know, it's 5 times the cost and it's not actually going to arrive. You know, some of the stuff is like 46 weeks and 44 weeks, and it's insanity, you know.
Agreed.
Wait, you know, it's going to be a year later. So anyway, you know, we work with what we've got and we do our best. And so, yeah, so it's actually on the pick and place now. There were some changes made to accommodate different parts, and different parts were brought in, and but yeah, we'll get there. So yeah, so that'd be fun to play with. And the wheels are, you know, it'll drive these. I don't know if you've seen these things. These are actually in the Powlex store now. I'm just about to completely wreck some edge modules if I bring this in too quickly. Because they are, I can't believe the weight of these things. But yeah, you're probably all familiar with these hoverboard wheels, but my gosh,
what you have to do, well, you saw our setup, right? We have a big vise that we set on the desk and we hold the wheel shaft in the vise. And then that, stabilizes it so we can hook up to the wires without spinning the wires around.
Yeah, well, I'll get Otto to make me up something that I can bolt onto the side of this desk. But we've got these really nice mounting brackets, which just clamp on there, and then there's
those were made right here.
Yep, next door to Chip.
Yeah, see, that's a good design that Doug did, because the flat, if you twist it at the right angle, you'll catch the flat on that top board. So spin the whole thing until you get the flat in the right place.
Oh, you're talking about on the
There you go. Yeah, see the flat is there. Yeah, now it'll work.
Okay, yeah, that's.
And then he's got about 20 mils. Oh, wait, turn it still minus 90 degrees or so.
Because the flat would be to the small piece, wouldn't it?
That's right.
And then we've got the mounting holes on this side to go down to the robot chassis.
But why isn't it clamping down? It should, you should hit a point where it just collapses and gets really close.
Yeah, I'd have to get my big head in there and have a look and see what I'm doing wrong.
It's the flat. Just put the flat. There you go. Yeah, now.
Surely it's that way, but that doesn't seem right. Because the flat's here, so the flat must be against this.
Yeah. But there's like 20 mils of slop in there, or slack.
Yeah. I mean, I might not have the same wheel as he had, because this might be a.
Man, well, we're in trouble if that thing is wrong.
Yeah, but this is not the main stock. This is just a. We'll check it, but it seems to go. It seems fine.
Okay.
It holds there, and then we've got the bolts. Oh, he's actually got mounting on both sides, so it's a left or right hander. Yeah. So just need to make up a chassis and have an experiment with that.
I'm a little confused on the naming convention. I see 3 big wires coming out of that motor, and we're calling it a 4-phase motor driver board. So is there an extra set of transistors on the board for some reason?
Yeah, this board will drive 4 phases, but those motors are only 3.
Got it.
So
okay, thanks.
Yeah, so you could run you could run 2 pairs of traditional 2-wire motors, for example, such as the Arlo robot brushed motors. And Chip, were there any other wheels you were targeting? I think this was just, the idea was just to be as universal as possible to support the old brushed motors as well as the new brushless.
Right. Yeah, that board can handle all kinds of combinations of things. It should be able to do any single motor around. It'll do a 4-wire stepper or a 3-wire BLDC motor, and then it can do 2 brushless or 2 brushed motors bidirectionally.
Yeah.
Because there's 4 channels. There are 4 half bridges on that thing.
Just make sure that makes it into the marketing, just to also explain the name. So if somebody's looking for a brushless motor driver and they're typically looking for a 3-phase one, they're not going to get confused being like, well, this work.
Yeah, it's really good. Good feedback.
Can we see the board model again, please?
Oh, I'm moving around on my screen thinking you can see it, and of course
We're watching the motor.
it is a private show.
Perfect. Now, each motor has that header for all Hall inputs. So if you were hooking up 2, what are we doing with the second header?
Okay, so you can only drive one of those big chunky wheels from this. So if you want to run 2 brushless three-phase motors, such as the hoverboard motor, then you'd need 2 of these breakout boards.
Okay.
Yeah.
Thank you. That helps.
Are there any other features like overcurrent protection or thermal shutdown?
I think it's built into, well, let's see. I don't know. Do you know? Michael would know. You don't-
I didn't prepare myself to show this really, other than just thinking, oh, it's just popped up. And it was so long ago. I know the control chips do have various protections in them. I just can't remember what, but I'm just having a quick look now. We'll show this properly in a week or so, or probably next week.
It'll shut down and not burn itself up, but and then just cool down and work again.
Yeah, it's got some sort of overload, and it's probably got over temperature protection, I suspect, which is typical nowadays. So yeah, it'll probably shut down once it gets too hot.
Yeah, Michael, on the website, there's a picture of the wheel with the Hall effect inputs, the wiring. And it's yellow, blue, green, phase 1, phase 2, and phase 3, and the board has UVW. I don't know, you might want to kind of have those agree. See that UVW up there on the header, the Hall inputs? And then you go to the motor. The picture of the motor has like a header with yellow, blue, green, and phase 1, phase 2, phase 3.
Yeah, that's a really good point as well. I mean, the reason that the UVWX came about was because that was handed to me as a kind of standard for these 3-phase motors, or 4-phase, to go UVW, and then X was added on as the 4th. And we do know, when we looked at it, that the coloring of these commodity motors is not always the same. So some will be some will be green, yellow, blue, some will be blue, yellow, green. I think the best ones are in alphabetical order, because then it's easy to remember. But they do vary. And what I found was that the way most times to tell the order of your wiring is just to look at the hall sensor cable, because as long as they've assembled it the same, you could start from the positive red cable, and then your order on this one is going to be yellow, blue, green, and then your phases are in that order. But unfortunately it does vary. So that's partly why we didn't want to label the board with colors, because this isn't something we can control.
Oh, that's good. That's good information there.
But that's definitely something that will be in the product guide.
Good deal.
To explain the coloring thing. We sort of agonized a bit over the coloring, but unfortunately, it's just the way it is. Unfortunately, it's not, unless you times 3 the price of the motor and have your own custom made source, it's difficult. Chip, where did the UVW come from, though? Do you remember?
I think it's just some old convention for, it's used for vector, to express vector stuff, which is how these motors are in principle. So U and V is used in PAL TV, whereas we use I and Q for NTSC. So UV and W being a 3rd phase was just the next letter after V.
Funny thing about that is that a lot of devices don't actually use YIQ, because the property of YIQ is that you can basically get YUV by just rotating it in phase. So for some reason, a lot of devices just skip that YIQ and just do YUV, but shift the color carrier a bit around. And
It actually made me think as you were saying, as you were explaining that I do wonder with the P2 if it's almost capable of figuring out the phases by itself. I suppose it still needs some human feedback, but because
it should be.
Because
you just switch one of the leads if it's going the wrong way. So
yeah, but
sensor feedback, you could get it to do that through software.
Yeah, do it through software. Yeah. So that could be quite neat. That could be a really unique, P2 only, or for this motor controller only thing that others can't do.
But a lot of the brushless motors that people will be using this for aren't going to have the Hall feedback. So.
Right. Yeah. The Hall.
Yeah.
Yeah. Especially smaller motors. So for those, we'll need to have some kind of field-oriented control worked out. We have, Michael, that we have here, okay, we have 16 pins, right, that we're using. We have, how does it work? I'm trying to remember, we have for each leg or each half bridge, we have 2 pins, right? So you can, one going high will cause maybe the end FET, the bottom FET to fire, and then the other one going high will cause the top FET to fire. But those chips, fortunately, have some kind of logic in them so that if you put both high, they don't just create a short from power to ground. That's like the biggest potential for fire in this thing is if you were to turn both legs of those on. But these driver chips, I'm sure they don't permit that. See, they have the HO and LO outputs, and they have the HI and LI inputs.
Yeah, that's the whole point of the driver chip, really, is to ensure that the one's only on and one's only off, and the timing between that transition is maintained. Right,
and that the gate drive voltage for the top end FET is above the source voltage. We actually above the source and drain voltage. And this also lets you use NFETs because typically, well, the old days, they'd always use a PFET on top, NFET on the bottom. But now it's great to use 2 NFETs because they have better conduction than PFETs. So you get a little more for your money.
Yeah, less series resistance and yeah.
That little HBHS cap is what allows, it's like a charge pump from that is used to hold the voltage for applying to the HO so that you can get it above drain and source to turn it on.
Yeah.
Anyway, so there are 4 of those on this board, and you can see that you'd need 3 of those to run a BLDC. Okay, and then we have the feedback. So we have 8 pins that are concerned with the high and the low. drivers for each of the 4. So that's 8 pins. And then the other 8 pins, we have 4 of these sense points.
Yeah, on the other header. And then the common is the 5th, and then 3 Hall inputs, 6, 7, 8.
Okay, yeah. So we have, okay, yeah. So we have sense for U, V, W, and X. And then we have a common sense. And then we have the Hall effect inputs and there are 3 of those. So that if we're using this hoverboard wheel, we can know exactly how to apply power to it. Via the
Good call on putting common sense into this board.
Yeah, we tried. It's all the common sense we could muster.
There's a nice little diagram there. Pretty much shows what's going on.
Oh, did you make this, or is this?
No. It's in the data sheet for the driver.
Oh yeah, that is pretty much like what we have, except we don't have the buck regulator on. So you just have to hook a big power supply onto 2 of those screw terminals.
Yeah.
And
Yeah.
what is the power input range for this? Oh, 6 to 40. I see.
Yeah. Yeah, and we specified these really chunky terminal inputs with sprung clips, so you don't have to mess around with screwdrivers in the classroom. Yeah, it's super high current, very chunky.
If anybody does electrical wiring at home and stuff, use lever nuts these days. I'm never going to do wire nuts again now that I've started using those things. They're miracle.
Yeah. Yeah, they work really well. Lots of LED drivers use them as well. Same sort of thing. Although I know when they first came out in manufacturing, although it's a slight tangent, they were sometimes a bit tricky to have soldered on the board without them melting down, because the extreme heat sometimes needed for lead-free, and also, you know, where the PCB board might have large copper planes, you know, because of the current, to meet current ratings. Yeah, they could be fun. So manufacturing, you need to get very high temperature versions. That's for sure.
This isn't quite the same, but these actually, on the little boards I made for my students, I use these Wago connectors. So it's just super easy. This was a common terminal bus for all the grounds. So you basically just throw a wire in, it can be stranded or solid, and just close down the lever and it just snaps it on.
Yeah. Very nice. Yeah, it's getting easier. Well, I think that's covered the bits I think that I could show today. Unless there's any other questions or any bits people might want to look at before I shut this down.
Michael, did you go? Oh yeah, go ahead.
No, go ahead, Chip.
I was just going to ask Michael if he reviewed like what the 6 connectors are. There's 6 wire terminals there.
Yeah.
It goes. Okay, so
the center 2 terminals are the voltage in.
Right. Okay. So ground and 6 to 40 VDC, because those have to be set. See, normal convention would be that you'd probably have that off to the side, but in a case like this where there's so much current that has to be, you know, moved evenly, and you don't want to have long traces. So that wound up in the middle, and then the U, V, W, and X wound up on the edges, or out of the middle.
Yeah, that comes out. So that, yeah, so the voltage path, exactly that. It comes in, goes, if you like, it's a sort of a T shape. So it goes round the back here, into the back of the drivers and straight into the MOSFETs and then straight back out again. So there's a really tight loop for the high voltage path round that way, and then also round, round to the, depending which way I turn my head, round to the left and round to the right. So yeah, voltage in the middle and then straight back out the two sides, equidistant, as short and tight as possible.
What's going to be the maximum current rating for this?
We need to kind of test it. I think provisionally we were saying 20 amps.
Yeah, we don't, yeah, I mean, it looks fantastic, but from just looking at the components and what they're capable of, but the trouble is we don't know practically what this means when we start switching all that power. And I think that the big issue is going to be not switching like if we had heater elements out there, man, we could switch all kinds of power and not get hot at all. But the motors have inductors in them and they create, what do you call it? EMF?
Back EMF.
Back EMF, which is like this giant load dump that comes and it gets caught. Can you zoom in on those FETs? It gets caught by the FET, the diode in the FET. You see those diodes in the FET? So when that back EMF spike comes, it conducts across that diode. The trouble is that diode has like how much volt drop? Is it like 1.4 or something, or is it less than a volt? You remember, Michael?
I don't remember, but it's probably less than a volt. It's probably closer to, yeah, it's probably more like
let's say it's
0.7, 0.8.
Yeah, so let's say it's 0.7. Well, and so what happens when that EMF dump occurs is that spike is that a lot of current gets compressed into a little time because the field's collapsing. So there's a lot of energy released. So it dumps a lot of, that thing's going to dissipate a lot of power. So the heat the MOSFETs will get hot because of back EMF, not because of switching the power, but because of when it unswitches and those coils release that energy, it gets absorbed ultimately by the power supplies, but not before passing through the diode in the FET, which is going to heat the FET up, which is going to heat the circuit board up, which might make it too hot to touch if you're running the motor, continuously. We'll see. That's the part we don't know. But yeah, I mean, we were calculating like, well, gee, this should do like, was it 500 or 1,000 watts, like a whole horsepower? It just doesn't seem possible, but the conduction is good enough on the FETs to do that. But I think the back EMF is going to be the limit, the big limiter.
Yeah, and that's totally something we need to experiment with.
Yeah.
So
You might want to just throw in a couple adhesive heat sinks as part of the kit. Again, I put some of these on the P2 Edge modules just to kind of make them look cool for my students, like Ferraris or something. But when you buy microstepper drivers and stuff from Amazon, they come with little adhesive aluminum heat sinks to stick on top of the MOSFET or the driver chip. It might help. Might give you a couple more amps.
Yeah. Well, we'll see how we go. It's not a bad thing. Gosh, they'll be teeny to get in there and not short out on the passive components. But yeah, I mean, we've made the copper really thick. The PCB is really solid. It's 2 ounce top and bottom, and it's also got the 2 inner layers are probably 1 ounce each, but one of them is also bolted down to ground, and we've got the planes all going out to the edges. So we've tried to maximize the path for the heat dissipation as much as possible.
Also, Parallax seems to have some aluminum CNC capabilities. Maybe there's a special custom C-shaped thing that just fits into the screw mounting holes and goes around and taps onto each of the chips with some heat adhesive thermal strip that just lets it be twice as powerful. Just as another option.
Yeah.
Of course, you can always put a brushless motor fan on it too to cool it down all the time.
Yeah. Yeah, it might work out. And this is going to be I mean, the main thing here is not for this to be delivering huge power. You know, this is going to be, you know, it's not the intent that this is to, you know, do crazy things, but this is certainly going to run, you know, moderate motors really well. And the idea is we'll learn from this then and build a really stonking motor controller later, probably with more phases to be able to run a pair of those hoverboard motors at full lock. But this will enable us to kind of experiment and to figure out, you know, where those limits are. Yeah, and actually the MOSFETs that we've included in the first run, because I was sort of, these were replaced with, I think they're 85 amp rated MOSFETs in the final edition. So there are sort of even some improvements from this, but the limiting factor is still going to be, you know, the copper really, and how we can get the heat out. So yeah, and hopefully it won't melt these plastic parts.
Yeah, those wire terminals would probably be the first thing to just get soggy and droopy.
Gooey. I know,
Yeah.
just as an anecdote, I know with the DHB10 motor controller, which I've got one here, just by luck. This was rated for 20 amps. Got it upside down there. But I was testing this with some 12-volt halogen flood lamps, which I believe were 30 amps, and it was pulling something like 30 or 35 amps when the fuse holder started to melt. And I kind of picked it, well, I didn't really pick it up, but I kind of touched it just to feel how hot it was, which obviously is a really stupid idea, to touch it with your hand to see how hot it was.
That's what I do.
Yeah, but that was the initial instinct, and the fuse holder just clean came out. It just dropped out. So actually, the solder had melted.
Yeah.
And
what good is the fuse if the solder fails first?
Yeah, but what was interesting in the end, in the final kind of analysis, was that this component here is a PFET, which was only really installed for reverse polarity protection, but it worked as a really good heater. So the H-bridge MOSFETs actually were running relatively cool, and they could handle the current no problem. But this PFET in here was heating up so much that it actually melted the size of the fuse holder and the actual casing of the yellow fuse. And then it got to and then obviously it ran away and got to a point where it melted the solder. It's quite possible that the prototype was made with leaded solder, so possibly a lower melting point. But anyway, yeah, running these into resistive 35 amp load is not really a great idea, but yeah, it's fun to see components melting. But size-wise, actually, the new board is not far from this. So that's actually another kind of, you know, we've used thicker copper than on this, or at least a larger area. So yeah, so that's also another sort of reasonable indication that we'll be good at the higher currents. Sorry to go off at a tangent there. Just came to mind. Yeah.
So we might have these in a few days, huh? To try out.
Yeah, I mean, they're literally loading on the PMP, the pick and place machine today.
Let me see if, let's see.
That was the message I got just 20 minutes ago or something.
Oh, Terrell, here we go. Okay, I should be able to pick and place a panel before 4 p.m. today. What time is it now? It's 2:46. Okay, I'll run the panel to the selective solder machine, then we'll have Chantel ship them to you. How many do you need? There are 6 per panel. Should we send some to Michael? Okay, what do I tell him? Said, I would like 2, please. Michael needs 2 also. Is that right?
Yeah, I'll drop Chantel an email as well to get some other bits.
Okay. Oh, yeah. Well, she's on this. Oh, she's on this thing. You might be on it too. Let's see. Okay. All right. There. Hit send. Okay, done.
Awesome.
Okay, so the last item we have on the agenda is updates from Chip. Do you have any?
Not really.
Okay.
I'm still working.
No
on-
curry sauce, no curry sauce. Unbelievable.
Oh, okay. So here's what happened, Ada. So I've got this thing in a state of flux again, and it's kind of like ripped apart and broken, and I'm getting it back together. So I'm putting the stuff in to allow like a cog that is in a debug interrupt to ask a quick question, and if the PC, and if the answer is wait, then it has to go back, release its resources that it's stopping other cogs from being able to use, do some kind of delay, and then wait for the lock again, and then try to have the conversation again. So I'm working on that part right now. So when that gets working, I will put everything together, but I'm sorry, I tore into it before I got the whole thing posted on GitHub.
Can't you just like post the previous version in the meantime?
Say that again?
Can't you just like post the previous version in the meantime?
If I can piece it back together, right now I've like broken everything.
You don't have any sort of version control?
No, Ada.
Well, I got away from floppy disks and now I use GitHub. But it's just, there's all kinds of junk in that folder. That's why I made a special GitHub folder just for Peanut that other people will use, because you don't need, I mean, I've got probably 600 files that are who knows what. So I
Yeah,
have to make like,
if you just put lots of stuff into the repository, you can't really, the problem is you can't like remove files from the repository after the fact without it being like a huge thing and breaking all your references. That's kind of the downside of Git, really.
yeah.
Since you don't have anything to say, anyone want to see my silly video nonsense? I've got it in a thing.
Okay, should I stop recording at this point?
You may, or how much time have we got on the recording now? An hour 49?
Yeah, roughly.
Well, let's ask Ada, you want to be on YouTube?
Maybe, I don't know. I posted this stuff on the forum already, but
okay,
it's nice to see.
Okay, so then you can cut it off. Andy, that'd be fine.
Okay.
Is that right, Ada?
Yeah, it's fine. Everything's
Okay.
fine.
Okay, here we go.